Okay, so we've all seen them, right? These massive, kind of graceful giants turning slowly way out on the horizon. You see them and you think, clean energy. But what's really going on inside? Well, it's this incredible mix of physics, aerodynamics, and some seriously cool engineering.
So, how in the world do they take something you can't even see, the wind, and turn it into something we use every single second, like the lights in our homes? That's the big question we're going to tackle today. We're going to follow that little gust of wind all the way from the sky, through those giant blades, deep into the guts of the machine, and right out onto the power grid.
All right, first things first, we got to talk about the fuel itself, the wind. And it's kind of funny, but wind is really just a form of solar power. Think about it. The sun beats down on the earth, but it doesn't heat everything up evenly. So you get these pockets of hot air and cold air creating high and low pressure. And what does air do? It rushes from the high pressure spots to the low pressure ones. That rush, that movement, well, that's kinetic energy. And that's exactly what we're trying to catch. So to figure out just how much energy we can actually grab, we have to turn to a little bit of physics. Now, don't worry, this equation looks kind of scary, but it's the key to everything. You've got P for power, rho for air density, how thick the air is, and A for the huge area the blades sweep. But the one part you really need to pay attention to, the absolute game changer in this whole thing, is V. That's the wind speed. And here's why that little V is so important. Look at that tiny number next to it. It's cubed. That's not V squared. It's V to the power of 3. And that is everything. It means the power you can get isn't just a little bit more when the wind blows a little faster. No. It's proportional to the cube of the wind speed. And honestly, the impact of that is just massive. Let's put that into perspective. Look at this. If you double the wind speed, say it goes from 10 miles an hour to 20, you don't get double the power. You don't even get 4 times the power. You get 2 times 2 times 2, that's 8 times the available power. It's incredible. And that right there is why companies are so incredibly picky about where they build these wind farms. A tiny bit more wind on average means a whole lot more power. Okay, so you might be thinking, why not just build a giant wall that stops the wind completely and grabs 100% of its energy? Makes sense, right? But it doesn't work that way. Way back in 1919, a physicist named Albert Betz figured out why. If you stop the wind dead in its tracks, the air just piles up. It creates a traffic jam and no more wind can get through. He actually did the math and proved that the absolute maximum, the physical limit you can ever hope to capture is 59.3%. And get this, modern turbines are already hitting 40 to 50% efficiency. They are literally pushing the boundaries of what is physically possible. So we know there's a ton of energy in the wind, but how do the blades actually, catch it? Now, the image most of us have in our heads is of an old Dutch windmill where the wind just pushes on the blades. But that's not what's happening here at all. That's one of the biggest misconceptions about wind turbines. The truth is way, way cooler. The real secret is lift. We're talking about aerodynamic lift, the exact same force that lifts a massive jumbo jet into the sky. A wind turbine blade isn't a sail being pushed, it's a wing. It's an airplane wing, basically, but instead of being designed to fly up, it's designed to fly around in a giant circle. So how does that even work? Well, it's all about the shape of the blade, which is called an airfoil. See how it's curved on one side and flatter on the other? As the wind hits it, the air that goes over the curved top has a longer journey, so it has to speed up. And here's the magic part. Bernoulli's principle tells us that faster-moving air has lower pressure. So now you've got high pressure under the blade pushing up and low pressure over the blade pulling up. And that difference? That's lift. It's a force that literally yanks the blade forward and gets the whole thing spinning. But of course, it's not that simple. There's always a battle going on. You've got 2 forces at play here. Lift is our hero. It's the force that's making things go, driving that rotation. But then there's the villain, drag. Drag is the force that's trying to slow everything down. So the whole game, the entire science of blade design, is about one thing, creating a shape that gives you the most lift possible with the least amount of drag. And believe me, these blades are not just simple, flat pieces of fiberglass. They're incredibly complex, sophisticated pieces of engineering. For one thing, they actually twist from the base to the tip. Why? Because the tip of the blade is moving way faster through the air than the part near the hub, so the angle has to change along the whole length to keep catching the wind perfectly. They also taper, getting thinner towards the end. That helps with stress, and it also makes them quieter. Literally every single inch of these blades is optimized for performance. Okay, so we've got the blades turning. Awesome. But here's the problem. They're turning really slowly. We're talking like 15, maybe 20 revolutions per minute.
That's stately. But a generator, the thing that actually makes the electricity, needs to be screaming along at something like 1500 RPM or more. So how do you bridge that massive gap? How do you turn that slow, powerful spin into a super fast one? To find out, we have to go inside that big box at the top, the nacelle.
Well, turns out there are two main ways to solve this problem. The classic approach is to use a gearbox. It's basically like the transmission in your car, with a bunch of gears that take the slow input speed and ramp it up to a really high output speed. It works, but gearboxes have a lot of moving parts, and that means more maintenance. Then there's the newer, more elegant solution, direct drive. This design just gets rid of the gearbox completely and uses a huge, special kind of generator that's designed to work at slow speeds. Now, because they're simpler and way more reliable, these direct drive systems are pretty much the go-to for offshore turbines. I mean, can you imagine having to send a repair crew out on a helicopter in the middle of a stormy sea just to fix a gearbox? No thanks.
All right, so now we're generating electricity, but we've hit another snag. The wind never blows at a perfectly steady speed, right? It gusts, it lulls, and because of that, the electricity coming out of the generator is, well, it's wild. The frequency, the voltage, it's all over the map. You can't just dump that onto the grid. It's messy. It needs to be tamed, cleaned up, and made presentable.
And the kind of generator you use actually plays a big part in this. A lot of turbines use what are called doubly fed induction generators with electromagnets. They're good. But the state-of-the-art tech, especially in those direct drive systems we just talked about, is the permanent magnet synchronous generator. The name's a mouthful, I know, but the key is permanent magnet. Instead of using electricity to make magnets, they just use really, really powerful magnets. This makes them more efficient and, more importantly, more reliable because they don't have parts called brushes that wear down over time. It's another piece of the puzzle for making turbines that can run for years without a lot of fuss.
So how do you tame that wild electricity? It all happens inside a box called a power converter, and it's a neat three-step trick. Think of it like a water filter. First, they take that messy, variable AC power from the generator and run it through a rectifier, which turns it into smooth, stable direct current, or DC. That's step one, get it clean. Step two, that DC power just chills for a second, totally stable. Then, in step three, they run that perfect DC power through an inverter, which flips it back into AC. But this time, it's not wild anymore. It's a perfect, clean, beautiful sine wave, humming along at exactly the frequency the grid needs, 50 or 60 hertz, depending on where you are. Perfect, grid-ready power.
So there you have it. We've followed the journey from a simple breeze all the way to useful watts on the grid. But a modern turbine isn't just a dumb machine, oh no. It's basically a giant, intelligent robot that's constantly thinking and adjusting. And on top of that, the whole industry is working flat out to innovate and solve some of its biggest challenges, especially when it comes to the environment. Think of this thing as having a brain. It's got two main systems that are always at work. First is the yaw system. That's what's constantly sniffing the air, checking which way the wind is blowing, and physically turning the entire head, the nacelle, to face directly into it. It's always chasing that maximum power. But maybe even more important is the pitch system. This system can change the angle or the pitch of each individual blade. When the wind is just right, it sets the perfect angle for power, but when a huge gust comes through, it twists the blades to spill some of that wind, kind of like letting out a sail. It's a brilliant safety feature that protects the turbine from tearing itself apart.
Now, let's be honest, one of the big concerns with wind turbines has always been their impact on wildlife, particularly birds and bats. But the industry is coming up with some really clever solutions. Check this out. A simple fix, painting just one of the three blades black, has been shown to reduce bird collisions by over 70%. It just makes the spinning blades more visible. For bats, which hunt at night, some turbines now have ultrasonic deterrents that create a high-frequency sound field that bats don't like, so they just stay away. And now we're even seeing AI-powered systems with cameras that can identify a protected species, like an eagle flying nearby, and automatically and temporarily shut the turbine down until it's passed. It's pretty amazing tech.
Okay, but what happens when a turbine gets old and needs to be retired? For a long time, the blades were a real problem. They're made of these super strong composite materials that are a nightmare to recycle. But that's changing fast. The industry is tackling this head-on. One solution is to shred the old blades and use them as both fuel and a raw material in cement kilns. Pretty cool. More advanced methods like pyrolysis use chemistry to break the blades down and recover the valuable glass or carbon fibers so they can be reused. But the real holy grail is what's happening right now. Companies are inventing brand new types of resins so that the blades of the future will be 100% recyclable right from the get-go. It's all about creating a closed loop.
So, when you step back and look at it, from the elegant physics of aerodynamic lift, to the smart systems that protect wildlife, to creating fully recyclable materials, the modern wind turbine is just a genuine marvel of engineering. And they're only getting bigger. I mean, the newest offshore turbines are literally the size of skyscrapers, reaching up to catch winds that are stronger and more reliable than anything we can get on land. It really makes you wonder, right? As these incredible machines continue to grow and evolve, what's the next big challenge they're going to solve?